So, my name is Beate Heinemann. I'm Director for Particle Physics at DESY, and it's a huge pleasure for me to welcome you all to this very special event. It's actually triply special. It's a DESY colloquium. It's a colloquium of the Wolfgang Pauli Center, and it is the opening lecture of Edward Witten's Wolfgang Pauli Center Masterclass lectures, for which 300 students have registered. So I want to especially really welcome all the students. I also see that this is a very young audience. I would say the average age is certainly much lower than mine. And I'm really excited. It shows that this is really a mecca for physics, Hamburg, that there is this huge interest in physics, and that we have, I think there's even more people on Zoom, like 100 more people at least on Zoom. So welcome. Okay, so we have, of course, this is thanks to our very distinguished speaker today. So Edward Witten, he was born in Baltimore, Maryland. He then actually did his bachelor at Brandeis University in history in 1971, but then switched to physics, which he studied at Princeton, first in master and then later in PhD, and got his PhD in 1976, actually working with under the supervision of Nobel laureate David Gross. He then became a postdoc and junior fellow at Harvard University in until 1980, before becoming professor at Princeton University. And then since 1987, he's actually the Charles Simonyi Professor for Mathematical Physics at the famous Institute of Advanced Study in Princeton, which is also where, for instance, Einstein spent most of his time after immigrating into the United States. He has many awards. In fact, there's more than 4 pages of awards, and I don't want to take away from the science, so I'm just highlighting a few of the awards. He has won the Fields Medal, the Lawrence Medal, the Isaac Newton Medal, the Breakthrough Prize for Fundamental Physics, the first one in 2013. Actually, I remember that. I was at CERN at the time. There was also Nima Akani Hamed won it, and I think Juan Maldacena also at the same time, and also Stephen Hawking, actually, that year won it. And last but certainly not least, he also last year won the Hamburg Prize for Theoretical Physics, and we're very happy about that. He has accomplished a lot scientifically. He's known as the architect or founder of string theory, the father of string theory. Also the founder of what's sometimes known as physical mathematics, which means to use actually quantum physics to gain insights into mathematics. And that's also particularly why he got the Fields Medal for. And he's also pioneered many novel and fascinating insights into the quantum world through exploiting and exploring dualities. And most recently, and I suspect that this is what the talk is about, is to really also use the understanding of black holes as probes for quantum gravity. And quantum gravity is really one of the big challenges that we want to understand. So I'm really delighted to present to you now Edward Witten, and thank you very much. Thank you.
Well, thanks very much for the invitation tonight and for all of the kind words we've just heard. I won't engage in any fact-checking concerning possible exaggerations. So as you can see, my title is Invitation to Black Hole Thermodynamics. And I've tried to make a lecture that makes sense as a standalone lecture, but also that for those who want to go farther on this week, is the beginning for a series of 7 lectures that I'll give the other 6 in the next few days. So if there's one thing that almost everyone knows about a black hole, even if you're not a physicist, it's that entering a black hole is a one-way street, a trip with no return. What goes in does not come out, at least according to Einstein's classical theory. for a black hole to capture something is irreversible. But there's a conflict between such irreversibility and basic principles, which say that, first of all, the laws of nature are completely invariant under time reversal, as a 19th century physicist might have said, or as we might say more precisely today, under CPT. And more microscopically, assuming that nature is described by a Hermitian Hamiltonian, if there's a matrix element for transition from a state psi to a state chi, then there's a complex conjugate matrix element for transition in the opposite direction. So nothing can be truly irreversible, although unfortunately the last part of that sentence is below the screen. Now, of course, although as I just told you, nothing can be truly irreversible, we see irreversibility all the time in everyday life. For example, when we break an egg, that's irreversible. There's even a famous nursery rhyme about it in English, where, again, the rhyme is a little bit cut off at the bottom. But anyway, Humpty Dumpty, seen as an egg, falls off the wall and breaks, and all the king's horses and all the king's men can't put Humpty Dumpty together again. Well, first of all, the king's horses and the king's men probably lack the technology to manipulate matter at the atomic scale. But even if they could manipulate individual atoms, it would be prohibitive to manipulate the Avogadro's number of atoms making up the egg in the precise fashion that would be needed to put all the individual atoms and molecules in a precise initial state so that the egg would spontaneously reassemble and jump up on the wall. That would require a prohibitive amount of fine-tuning, even if you do have the technology to understand and manipulate individual atoms. Now, as we all know from our study of undergraduate physics, the understanding that emerged in the 19th century is that the apparent irreversibility of everyday life is probabilistic in nature. The laws of nature do have solutions in which the atoms come together and recreate the egg and jump up on the wall. But such solutions are incredibly fine-tuned and very unlikely to be witnessed in practice. The basic idea of black hole thermodynamics is that the irreversibility that we find, according to Einstein's theory in black hole physics, is of the same nature as the irreversibility of everyday life. It's probabilistic and describes what will happen for natural initial conditions that we expect to be relevant in the real world, but not for very special fine-tuned initial conditions. If you drop a table or a chair into a black hole, it's very unlikely that the black hole will spit them out the next day, but it could happen with a positive but prohibitively small probability, similar to the probability that the broken egg on the floor will spontaneously reassemble and jump up on the wall. Now, if this is true, it means that Einstein's theory of gravity, general relativity, his greatest creation, is in some sense describing the average behavior of matter, not the microscopic details. Stated this way, there's no surprise, as in any event, Einstein's theory is purely classical, and there's nothing of the microscopic details of quantum theory that are important for describing at the atomic level the reversible and irreversible processes that we know. But there is a surprise, though it's a little difficult to fully explain in today's colloquium, and I think it's even a little bit difficult to fully explain in the whole series of lectures this week. But the surprise that one comes to appreciate as one grapples with this subject, the best way I could think of saying it is that Einstein's classical theory, in some mysterious sense, seems to know that it's giving a sort of average description of quantum behavior. The surprise isn't so much that Einstein's theory, being a classical theory, doesn't know the microscopic details. The surprise is more that it seems to know more than you would think about what the microscopic details will turn out to be. We'll see a little bit of that tonight and a little bit more in the rest of the week. There presumably is a deep lesson in this, though for now still a mysterious one. Now, of course, the other side of the relation of Einstein's theory to quantum mechanics is that, in fact, because of ultraviolet divergences, it doesn't appear possible to quantize Einstein's theory in any obvious way. String theory has been developed in large part because it overcomes this difficulty. But again, the deeper lesson about string theory for the nature of quantum spacetime is still murky. Ideally, somehow the unsolved problems in string theory and black hole thermodynamics would make contact with each other, with maybe each one providing a key to understanding the general lesson we should be learning from the other. But whether that's true or not, I can't say. But anyway, for this week, I will just be trying to explain the ideas in black hole thermodynamics. Now, we recall from our undergraduate days that the basic understanding of irreversibility in everyday life is that an irreversible process is one in which the entropy increases. So Carnot and others discovered the notion of entropy by purely macroscopic reasoning with no microscopic understanding at all. Just starting with the fact that there were irreversible processes in nature and postulates such as the impossibility of making a perpetual motion machine that extracts heat from the ocean to do useful work. It was understood that there had to be some quantity S, which is constant in reversible processes, increases in irreversible ones, and never goes down. But ultimately, by the end of the 19th century, the microscopic nature was understood. The entropy S is the logarithm of the number of possible microstates of a system once one has described its macrostate. So the second law says that in processes that we can observe in practice, the entropy is non-decreasing. Irreversible processes are those in which S increases. Processes in which S would go down are consistent with the laws of nature, but are prohibitively unlikely in practice. As you again can't quite see at the bottom of the slide. But maybe the people on Zoom can see the bottom. Not quite. However, Jacob Bekenstein, inspired by questions from his advisor, John Wheeler, observed that the second law appears to be violated when matter interacts with a black hole. If we toss a cup of tea into a black hole, the entropy seems to disappear. Bekenstein wanted to generalize the concept of entropy so that the second law would hold even when the cup of tea falls into the black hole. So for that, he wanted to assign an entropy to the black hole in such a way that the black hole entropy would go up when the black hole, when you toss the cup of tea into the black hole, you lose the entropy in the cup of tea, but the black hole entropy was supposed to go up by more. Roughly, he thought the black hole entropy would keep track of the number of ways the black hole could have formed. Well, what property of a black hole can only increase? It's not true that the black hole mass always increases. For example, if you have a rotating black hole, it can lose mass as its rotation slows down. And Penrose explained what you can do to make a black hole rotate more slowly. And in fact, this is believed to be important in understanding the jets that come from black holes at the center of galaxies. However, now you can't see the top of the slide. But however, just at the time of Bekenstein's work, Stephen Hawking had just proved the area theorem. The area theorem says that the area of the horizon of a black hole can only increase. The horizon is the surface of no return. So this is, so now I think you can't see it well because of the light in the hall. But this is supposed to be a picture of a computer simulation of a star field behind a black hole. And there's literally a hole in the image. There's a hole because the starlight that is incident on the black hole gets captured and doesn't reach us. So anyway, what you can't quite see here is a nice computer visualization of what it looks like when you're kind of seeing the horizon of a black hole in the light of stars that are behind the hole. But regardless, even people who aren't physicists have probably heard of the idea that the horizon is the surface of no return surrounding a black hole. And Hawking had proved that in the classical evolution of a black hole, according to Einstein's theory, the area of the horizon is non-decreasing. It can be constant, it can go up, but it can never go down. So that made the area a good candidate as the entropy of a black hole. So Bekenstein proposed that the entropy of a black hole should be a multiple of the horizon area. For example, according to Einstein's equations, a spherically symmetric black hole is described by the Schwarzschild solution with this metric. And in this case, the horizon is at little r equals 2 gm, and therefore d omega squared is the metric of a unit sphere. Multiplying it by little r, we get a sphere of radius 2 gm. So the horizon is just for its intrinsic geometry, is just an ordinary sphere of radius 2 gm. G is Newton's constant, m is the mass of the black hole. So the horizon area 4 pi r squared is 16 pi g squared m squared. And well, that's the horizon area for spherically symmetric black hole that sits there. If it absorbs matter, that'll be an irreversible process. M will increase and the area will go up. That's a special case of the area theorem, but the area theorem in general concerns black holes that might not be spherically symmetric. They might collide with other black holes. That they vibrate, they undergo dynamical processes. And Hawking showed that the area is always non-decreasing, just like entropy in thermodynamics. So looking for a quantity that could represent the entropy of a black hole, because he had the good fortune that Hawking had just proved this area theorem, it was fairly natural for Bekenstein to propose that the entropy of a black hole is a multiple of the horizon area. Now, since entropy is a pure number in units with k equals 1, Boltzmann's constant equals 1, but the area of the black hole horizon has dimensions of length squared, Bekenstein made use of constants, Newton's constant and h bar, to get the units right. His formula also contains the speed of light, but I'm setting it to 1. So keeping track of g and h bar, but not c, his formula was that the entropy is the area over a constant times g h bar, where actually the constant 1/4 was not clear for Bekenstein and was provided by Stephen Hawking a little later in a way I'll explain shortly. The fact that h bar appears in the denominator of the formula shows that the formula is fundamentally quantum mechanical. In part because h bar is so small in everyday terms, Bekenstein's, but more because g is so small by atomic standards, Bekenstein's proposed black hole entropy is very large. For example, a spherically symmetric black hole with the mass of the sun has an entropy roughly 10 to the 20 times the entropy of the actual sun. That means if a star collapses to a black hole, that's an extremely irreversible process, according to Bekenstein, where the entropy goes up by a factor of 10 to the 20 for a solar mass star and even more for a heavier star. So Bekenstein's idea was that the entropy of a black hole captures the information lost when the black hole was formed. He viewed it as the logarithm of the number of possible states that could have collapsed to form a black hole. And he proposed a generalized second law saying that the generalized entropy is always non-decreasing. So the generalized entropy was supposed to be the ordinary entropy S out of matter and radiation outside the black hole, plus the black hole entropy, which was for Bekenstein a multiple of A over GH bar. I'm writing it with the later discovered factor of 1/4. So he proposed that the generalized entropy always increases. So the claim was that when something falls into the black hole, S out may go down, but A over 4 GH bar increases by more. Now, Bekenstein tested the generalized second law in thought experiments with some success, but also running into a difficulty that I'll explain. And happily, the difficulty didn't discourage him from publishing the idea. I think it might have discouraged me, but who knows. Before getting into details, though, I should first make clear that in Bekenstein's work, by S out, he meant thermodynamic entropy. Ordinary thermodynamic entropy of Boltzmann, Cournot, and all the founders of thermodynamics was the only entropy Bekenstein considered. So in testing the generalized second law in Bekenstein's original formulation, we should assume that the inflowing matter is the system to which thermodynamics applies. For example, we can assume, well, the main example Bekenstein considered is that the black hole was absorbing a beam of black body radiation at some temperature T. Now, in 3-space, 1-time dimension, the relation between energy, E, temperature T, and entropy S in black body radiation is that the energy is 3/4 the temperature times the entropy. If a black hole of mass m absorbs energy E, which I'll assume is much less than m, from black body radiation, its entropy, which was this, so given what we found for the area, the entropy is 4 pi g m squared. It increases by approximately 8 pi g m times E. So that's the change in the black hole entropy. But the change in S out from this formula, when the black body radiation loses energy E, the change in S out is minus 4E over 3T. So the change in the generalized entropy is something that luckily I've rewritten on the next page. It's the energy times a constant by which the black hole entropy goes up minus a constant by which the energy of the black body radiation goes down. And you see the change in S-gen, the change in the generalized entropy is positive as long as the temperature of the black body radiation is such that the typical photon wavelength, which is of order 1 over T, is small compared to the size of the black hole, which is the black hole diameter is 4 GM. So if the black hole is absorbing radiation whose wavelength is less than the size of the black hole, then everything was fine and the generalized entropy increased. But delta S-gen is negative, violating the proposed generalized second law, if the temperature of the inflowing radiation is so low that that 1 over T, the wavelength of the inflowing quanta, are bigger than the size of the black hole. Well, in Einstein's theory, a black hole can absorb photons of wavelength much longer than the size of the black hole. Not very efficiently, but still it can definitely absorb them. So therefore, in Bekenstein's work, a process that violates the proposed generalized second law was possible. Bekenstein tried to address this, but I would say that the problem did not have a solution in which the framework Bekenstein assumed, which was that nothing ever emerges from a black hole. Given that assumption, I don't think this problem had a solution. In thermodynamic terms, since the black hole is assumed to not be radiating, one would have to assign it a temperature of 0. But then the first law, dE equals TdS, says that in a process in which the change in energy is positive, the change in entropy should be infinite, clashing with the fact that Bekenstein wanted to assign a finite entropy to the black hole. So in hindsight, the difficulty Bekenstein had with his generalized second law was that he was assuming that the thermodynamic temperature of the black hole was really 0 because his black hole was assumed not to radiate. And, well, given that T is 0, there's a clash between the finiteness of S and the fact that E can change. Now, famously, Hawking was skeptical of Bekenstein's idea, as you can't quite read up here. But in investigating the interaction of a quantum field with a black hole, he ended up proving that Bekenstein was right. And in the process, he made his greatest discovery. At the quantum level, a black hole is not really black. It has a temperature proportional to h bar. Bekenstein was clearly inspired with the work he did, but if he'd been slightly more inspired, he could have looked at this formula, dE equals TdS, and observed that since his S was of order 1 over h bar, as I showed you earlier, for dimensional reasons, his black hole entropy was of order 1 over h bar, and E of the inflowing matter was potentially of order 1. The black hole can absorb tables and chairs, classical objects whose mass energy we think of as having no h bar in them. So his temperature, so therefore he should have concluded that the black, well, I don't want to criticize Bekenstein because it was a brilliant epical paper. With 2020 hindsight, one might have concluded that to make this formula work, T should have been of order h bar. And then that is actually consistent with Einstein's classical theory. Then you'd say that classically, the temperature is 0 and the black hole does not radiate. But quantum mechanically it does with a temperature of order h bar. But prior to Hawking, nobody was inspired to think in that way, apparently. But Hawking discovered that at the quantum level, a black hole is not really black. It has a temperature proportional to h bar. And that turns out to eliminate the problems that Bekenstein had with the first law and also with the generalized second law. Now, as preparation for explaining Hawking's reasoning, I want to recall the idea of a Penrose diagram as a convenient way to depict and visualize spacetime. This is a bit of a problem because the diagram is slightly chopped off. I'm tempted to finish drawing it on the blackboard, but that won't work for the people on Zoom. So what a Penrose diagram is, I think I've got one on the next slide that won't be chopped off. What a Penrose diagram is, it's a schematic picture of it. You assume spherical symmetry. And then you depict space-time in a way you can conveniently see on the a sheet of paper or on the screen if it's not chopped off. And but usually you depict only time and one spatial coordinate, which you take to be a radial coordinate. You suppress angles. Okay, this is a better picture, so let's look at this one. This is the Penrose diagram of Minkowski space. So the radius is plotted from left to right. It goes from 0 on the left boundary to infinity over here. And time runs vertically. So time goes from minus infinity, only slightly cut off, to plus infinity. But a conformal mapping is usually made. Well, the main purpose of the diagram is to show causal relations. And the way causal relations are shown is that coordinates are chosen so that radial incoming or outgoing light rays are at a pi/4 angle to the vertical. So this purple line is meant to be at a pi/4 angle to the vertical, and it depicts an outgoing radial light ray. In other words, a particle escaping from near r = 0 at the speed of light. An ingoing radial light ray isn't drawn, but it would be at a pi/4 angle from the vertical, but in the opposite direction. And since causal relations are invariant under conformal mappings, a conformal mapping of the picture is usually made so that infinity is moved to a finite place where we can see it. So future null infinity, where a outgoing light ray would eventually reach, is this diagonal line, and past null infinity is this one. A massive particle begins life at the bottom of the picture, which is slightly cut off, and ends life at the top of the picture. And r = 0 is here. So many of you will have seen Penrose diagrams before, but for those who may not or who want a short refresher, that's the best I can do in a moment to explain it. Now, Hawking made his discovery by analyzing the behavior of quantum fields in a black hole geometry. So here I've drawn a Penrose diagram that shows a space-time in which a star emerging in the past collapses to form a black hole. The picture differs from the previous one mainly by the fact that there's this black hole horizon, this diagonal line, which is meant to be at a pi/4 angle from the vertical. And there's a singularity, this wiggly line at the top, schematically represents the black hole singularity. The gravitational field of the collapsing star created this black hole horizon. The star fell behind the horizon. It ended its life at at the singularity. And anyone who crosses the horizon can't escape, because the best you can do is to go outward at a pi/4 angle from the vertical, which, well, to the extent the picture is drawn carefully, would be parallel to this horizon, so you wouldn't succeed in escaping. So if you stay, a massive observer who stays outside the black hole horizon will end life at this point labeled I+, which represents future infinity. And what we're going to do in a moment is to consider the observations that would be made by an observer who stays at a safe distance. And this observer also waits until a late time after, there was a lot of commotion when the when the star collapsed to a black hole, but then the geometry settles down. And after transients die down, the observer will see what comes out of the space-time at late times. So, well, we could study the observations made by a distant observer at all times, but there will be transients that depend on the details of the collapsing star. Hawking discovered that what the observer will see at late times is universal, only depends on the mass of the black hole and not on the details of the collapsing star. Now, measurements that an observer at future null infinity, which is just a technical way to say an observer far from the collapsing star, also making observations at late time. So observations at the distant, let's just say a distant observer, that would be a less technical way to say it. Observations a distant observer will make can be traced back to any earlier time of our choice. So in blue, I've drawn an example of a space-like hypersurface. The hypersurface is space-like because its tangent is always at an angle to the vertical more than pi over 4. And it's useful to pick an initial time hypersurface that crosses the horizon to the future of the collapsing star. That means I've picked a blue hypersurface that intersects the horizon, well, outside of the world volume of the star. The red portion of the spacetime is the world volume of the star. So this blue hypersurface is chosen so that it crosses the horizon well after the black hole formed and after transients have died down. Now, signals might be emitted from the blue hypersurface and might reach the distant observer. And if that happens, assuming the signals are massless particles like photons, they'll travel to infinity at the speed of light, so they'll be represented by diagonal lines that are parallel to the horizon at a pi over 4 angle from the vertical. Those represent outgoing null signals, outgoing massless signals that might reach the observer at infinity, at which the observer at infinity will measure to see what's happening. Now, what will the observer see? Here finally is a picture where you can see the whole thing, by the way. So in this picture, the black hole, the star appears to have emerged at a point in the past. But that's an artifact of the conformal mapping used in drawing the Penrose diagram. The star was a star in the past. It had the radius of a star, whatever that is, maybe 1,000,000 kilometers in the case of a star like the sun. And then it eventually collapsed to a point in the future at the singularity after living a long life and eventually collapsing. And the collapse might have created a supernova with a lot of stuff coming out. But our observer is planning to make observations after all that chaos ends. So I haven't even drawn the chaos in this picture to not make it too busy. But important to us is that the observer is living way up here, which means far from the motion, but also at late times. And we'll look at quantum signals that emerge from the interior of the spacetime, but which we can trace from initial data on this hypersurface S. Causality says that we could trace what we observed from any surface in the past, and I've just picked one that will be convenient for the analysis. Now, part of Hawking's insight was that although the full details of exactly what the observer will see depend on the precise quantum state of the collapsing star, if we ask what the observer will see in the far future, after transients die down, we will get a universal answer. The key point about this picture is that a signal that's observed very late originated from very close to the horizon. That means that observations made at late times depend on measurements of the state of the quantum fields at short distances. But in quantum field theory, every state is equivalent to the vacuum at short distances. So the late time observations of the observer probe the vacuum state at short distances. Now, that's what physicists are trying to do at accelerators. And for example, at CERN, the vacuum is probed at distances of roughly 10 to the minus 17 centimeters, optimally, in the most extreme event seen at CERN. But, well, in a certain sense, observations of the signals coming out of a black hole very quickly probe the vacuum at distances much smaller than that. Now, okay. Here I've drawn the part of, okay. The previous picture was rather busy, this picture. And in the next slide, I'm going to draw a version of the picture that only shows the important bit. The important bit is the horizon, and then the far future. And the late time observer at a big distance is living up here. In this picture, it doesn't look like this is a big distance from the black hole. but that's an artifact of the conformal mapping that was used so that we can see the picture. So in this picture, I've taken u to be any coordinate that's 0 on the horizon and increases as you go outward from the horizon. And at late times, the observer will see a signal that originated at small u. So now let t be the time at which a signal is detected by an observer at infinity. There's no mystery about what we mean by t. Far from the black hole, the space-time is essentially Minkowski space. And t is just ordinary Minkowski space-time. It blows up near this corner of the picture because of the conformal mapping used in drawing the picture. U is, in some arbitrary units, the distance from the horizon at which the signal was emitted. T is the time at which it's absorbed. Remember that a signal from behind the horizon would never emerge to infinity. So a signal from very near the horizon will eventually emerge, but only at very late times. The essence of the Hawking effect depends on exactly how long it takes for a signal to emerge, depending on where it originates. This is a crucial thing. I hope this formula is on the next page again. Yeah, it is. Okay. So the crucial formula for the Hawking effect is the relation between T and U. And it was written here, but we'll see it again on the next page. The formula is that T is 4gm times the log of 1 over U, plus a constant that depends on how U is defined, plus a correction of order U. And we can also invert it to express U in terms of T. So as U goes to 0, the time at which the signal diverges, but only logarithmically. So that's a very slow divergence. But if you invert it, you get exponential decrease. So at a late time t, the distance from the horizon at which the signal emerged is a constant times e to the minus t over 4gm. So for example, in the case of a solar mass black hole, 4gm is, I forget, but something like 10 microseconds. So if you wait 1 second, this factor will be roughly e to the minus 100. So I can assure you that our experimentalist friends would be very happy if they could probe the vacuum at a distance shorter by a factor of e to the minus 100 every time they waited 1 second. It usually is much harder than that to probe the vacuum at very short distances. Now, this formula and also this one, they're the key to the Hawking effect. But unfortunately for today, I wasn't going to give a technical derivation. I will give one in the first lecture tomorrow. For today, we'll just accept that although the time at which a signal emerges diverges as u goes to 0, it only diverges logarithmically. And inverting that, we get this exponential sensitivity. So at late times, in other words, if t is large, u is exponentially small. So signals that a late time observer sees can be considered to have emerged from exponentially close to the horizon. And that also means there's an exponential redshift. So if you see a signal observing at late times at a reasonable frequency, it originated near the black hole at an exponentially large frequency. And as I've said a couple times already, a basic fact, but this time you can see it. A basic fact about quantum theory is that at sufficiently small distances, any state of the universe looks the same and is equivalent to the vacuum. So the late time observer is probing the vacuum at short distances. And that's actually why Hawking got a universal answer, independent of how the black hole formed. A late time measurement just probes the vacuum at short distances. Well, what does the observer at infinity measure? The observer probes outgoing radiation by measuring a quantum field that I'll call psi of t. In the real world, one would probably measure the electromagnetic field, but I'll consider a simpler model. And I'll take a couple minor shortcuts. Tomorrow, we'll discuss a more realistic model. A typical observable that might be measured is the correlation between the value of psi of t at 2 different times t and t prime. So in the real world, you'd be measuring the electric field, for example, and you'd want to know the spectrum of outgoing radiation as a function of frequency. And you would get that by Fourier transforming the 2-point correlator of the electric field at 2 different times. So a 2-point function of the electromagnetic field would give you the frequency of outgoing photons. But today we'll consider a slightly simpler model where we are measuring the 2-point function of a quantum field psi of t at 2 different times. So this correlator is called a 2-point function, and I'll denote it. The expectation value in the radiation coming from out of the black hole, I'll denote by the symbol as the expectation value of psi of t prime, in the state of the fields coming out of the black hole, whatever that is. Now, near the horizon, a quantum field typically has a power law singularity. Now, technically, I'm going to assume, okay, I should step back a little bit. Whatever, for example, if you're measuring the electromagnetic field, in the field of a spherically symmetric black hole, you could make a partial wave expansion and expand in spherical harmonics. Each harmonic would be a 1 plus 1 dimensional quantum field. After taking some particular spherical harmonic, you would have a field that still depends on time and also distance from the black hole, time and radius. So it would be a quantum field in the 1 plus 1 dimensional sense. And the typical behavior of a 1 plus 1 dimensional quantum field is to have a power law singularity. For brevity, I'm going to consider the case that the power is 1, but we could consider any power and get a similar result. Power is 1 if the 1 plus 1 dimensional field is a fermion of spin 1/2 in the 1 plus 1 dimensional sense. And then this denominator, numerator that might confuse you, du prime to the 1/2, is just a way to build in the fact that psi has dimension 1/2. So typically quantum fields have power law singularities at short distances. Here for simplicity, I'm just taking the power to be 1. And then, luckily we can see this formula. Then, using the fact that u is a constant times e to the minus t over 4gm, we see that for the observer at infinity, if I just change variables from u to t, we get a formula for what the observer at infinity will see. We get that formula. All I did was start with dimension 1/2, which gave du to the 1/2, a singularity with the power of 1, and then I changed variables from u to t, and I got this. Whatever I was about to say about it is cut off, but well, I guess what I next said was that this we now observe has the key property that it's anti-periodic in imaginary time. Well, it's anti-periodic because I took a model with a fermion. With a boson, it would have been periodic. In imaginary time. With the period 8 pi gm. I'm sorry, the people in Zoom probably didn't see me writing on the blackboard just now, but if you look at this formula, you'll see it's antiperiodic in T with the period 8 pi gm. And if I had taken u minus u prime squared, which would have been appropriate for a boson, it would have been periodic in T with the same period. Now, periodicity or anti-periodicity for bosons or fermions in imaginary time is the hallmark of thermal correlators, correlation functions, as you may recall from your study of quantum statistical mechanics. So what we learn is that a black hole, after transients that depend on how it was created die down, radiates thermally at a temperature T sub h, the Hawking temperature, which is 1 over 8 pi gm. Now, I've cheated slightly in the derivation, and we'll go over it at more length tomorrow. So the derivation I've explained is, in my opinion, the quickest way to explain the essence of the Hawking effect. You just start with the fact that a typical quantum field has a power law singularity. Then you change variables from u to t, and the power law turns into an exponential. And the exponential is actually periodic in imaginary time, which indicates a thermal behavior. So that's the essence of the Hawking effect. We'll go over it more slowly tomorrow and fill in some details. But what we learn is that a black hole, after transients that depend on how it was created, die down. We got rid of the transients by using the vacuum correlator of a quantum field, which was a simple power law. In the presence of transient behavior, there would have been some possibly more complicated behavior. But we learned that the black hole radiates thermally, and we can now confirm the value of the entropy. We use the fundamental thermodynamic relation between temperature T, entropy S, and energy E, dE equals T ds. For the black hole, the energy is its mass. The temperature we just found is 1 over 8 pi gm. So we learned that ds is 8 pi gm dm. So integrating that, assuming the entropy is 0 for a black hole of mass, when the mass goes to 0, there's no black hole, so we take the entropy to be 0. Integrating this formula from 0 up to mass m, we get that S is 4 pi g m squared. The area of a spherically symmetric black hole we computed before was 16 pi g squared m squared. So from this formula, we find that except that you can't see it, that the entropy is A over 4g. So I can write it on the blackboard, but I'm afraid I can't help the people on Zoom. So having determined the temperature, the first law and the knowledge of the area, which we computed before, tells us that the entropy is in fact the area over 4g. Now, you might be slightly unhappy about this derivation because miraculously the area came out, but the horizon area played no particular role in the derivation. Eventually, but not tomorrow, I'll give a derivation that does directly explain why the entropy is the horizon area. Now, because the black hole emits thermal radiation, the black hole loses energy, and in Hawking's language, it evaporates. But the timescale for the black hole to evaporate is very long. For example, a solar mass black hole takes about 10 to the 67 years to evaporate, assuming it's in vacuum. Of course, in the real world, a black hole is not in vacuum, and it would more likely accrete matter than evaporate. But in vacuum, a solar mass black hole would evaporate in 10 to the 67 years, way, way longer than the age of the universe, only about 10 to the 10 years. So we don't expect to observe black hole evaporation, unfortunately, unless we're very lucky. For example, if the black hole created very tiny black holes of just the right mass, for which there's no evidence at the moment. We do observe in cosmology something that's believed to be very similar to Hawking radiation from a black hole, namely inhomogeneities in the early universe that are believed to have been the seeds to formations of galaxies in the inflationary universe. The theory behind them is similar to what I've been telling you for radiation from a black hole, although we won't have time to go in that direction. Regardless of its applications to cosmology, Hawking's calculation is of great conceptual interest, and it's posed puzzles that have driven a lot of research in the half century since Hawking's work was published. In Hawking's calculation, the radiation that comes out of a black hole appears to be exactly thermal, with no correlation between the different particles that come out of the black hole at different times, except what follows from conservation of energy and from the temperature of the black hole. After all, the ideal calculation we did gave a pure thermal two-point function. And even improved calculations that I'll explain in more detail tomorrow give thermal behavior. If that's exactly true, it would mean that black hole evaporation cannot be described by fundamental microscopic equations that are invariant under reversing the flow of time. To see this, consider a process in which a star collapses to a black hole which then evaporates. If physics is really described by microscopic laws that are fully invariant under time reversal, then from the decay products of a black hole, it must be possible in principle to reconstruct the detailed quantum state of all the atoms in the star before it collapsed to make a black hole. One should then be able, in principle, to run the movie backwards and describe a state of the universe in which the outgoing decay products are reflected backwards, recombined to make a black hole, which then explodes to make the original star. So the state of the outgoing particles cannot just be purely thermal or random. There must be subtle correlations that contain the information needed to reconstruct the original star. But how that works in detail if you like, is the big mystery in black hole thermodynamics. Now, one basic clue is simply that black hole entropy is so big. For instance, as I remarked, the entropy of a black hole with the mass of the sun is much greater than the entropy of the actual sun. Now, many researchers have thought that somehow the entropy being proportional to the area means that the black hole can be described by some sort of degrees of freedom that live at its surface, with roughly 1 bit or qubit for every 4G of area. For example, in a famous picture in famous article in 1992, Wheeler, who'd been Bekenstein's advisor, illustrated that idea with this picture, most of which you can see. So he visualizes the black hole horizon divided in little bits of area of order 4G. And in each bit of area, he's placed a bit in the sense of computer science, a number 0 or 1. And if you read the article, you'll see that Wheeler imagined all these bits as resulting from measurements, for example, of a spin-half particle, what we now call a qubit, bearing in mind that the term qubit hadn't yet been coined in 1992. It might be that if you'd written the article a bit later, Wheeler would have said that there was 1 qubit for every 4G of area, roughly. Now, I've already mentioned that the Bekenstein-Hawking entropy is extremely large compared to entropies of ordinary astrophysical objects. It seems to imply that the number of quantum states of a black hole is incredibly big. Since ordinarily entropy is the logarithm of the number of states, consistent with the macroscopic properties. If that's the case for black hole entropy, then since the entropy is A over 4G, the number of quantum states of a black hole is e to the A over 4G. And since this entropy is so big, that's much, much bigger than any reasonable estimate of the number of quantum states available to anything else in the universe. So most of the quantum states of the universe are black hole states in some sense, if this is right. We don't have a very concrete understanding of this degeneracy even today, except in the important case of a supersymmetric black hole. But in the absence of supersymmetry, it's a mystery exactly how to understand this vast degeneracy. It's especially striking because in classical general relativity, there's a no-hair theorem going back to around 1970, which says that classically a black hole, once transients die away and the black hole settles down into a stationary state, is described just by the obvious macroscopic observables, the energy or mass, the angular momentum, and the charge. Those are the thermodynamic variables that describe a black hole. And the no-hair theorem says that once transients die down, a classical black hole is described purely by those thermodynamic variables. That might at first sight seem to be in jarring contrast with the claim that quantum mechanically there's an exponentially large number of states accessible. It might seem jarring at first, but actually in black hole thermodynamics, the no-hair theorem is interpreted in terms of thermalization. Ordinary matter shows a similar no-hair behavior. Take a cup of tea and pour it into a glass. For a while, it will slosh around, visibly not in equilibrium. After a while, the tea will settle down and reach an apparent equilibrium state, characterized for all practical purposes just by the relevant thermodynamic variables. The no-hair theorem says that a classical black hole does the same. So the no-hair theorem says that a classical black hole, after a while, settles down into a state that is characterized purely by its thermodynamic variables, namely the mass, the angular momentum, and the charge, the only conserved quantities that characterize the black hole. So black hole thermodynamics would tell you, well, if a black hole thermodynamics says that you should think of a black hole as being like any thermal system. So any ordinary thermal system, if you leave it alone for a while, will thermalize and will reach what will look for all practical purposes like an equilibrium state, characterized only by the conserved quantities and independent of the true microstate. So the cup of tea will be in apparent equilibrium, thermodynamic equilibrium after a little while. But if you could probe it at the atomic level, you would discover that there are many, many states, many, many microstates that look the same macroscopically, e to the s of them. So the fact that the cup of tea settles down into a state of thermal equilibrium is a kind of a state of apparent thermal equilibrium, is a kind of no-hair behavior. And black hole thermodynamics interprets the no-hair theorem of classical black holes to similarly represent thermalization. Now, what I've described up to this point is basically the concept of black hole thermodynamics as it developed originally in the 1970s. In the rest of the talk, I want to tell you just a little bit about more modern ideas, although we won't get very far. We'll get somewhat farther in the lectures the rest of the week, although we won't get completely up to date even then. So I don't know how long I'm supposed to go on, but I know that 6:30 was an unusual time for a colloquium to start. And I'm hoping that that means that I can go on for just a little bit longer than what might have been the planned hour. So in classical black hole thermodynamics of the 1970s, entropy was taken to be the familiar thermodynamic entropy. But in most of the developments starting in the 1980s, and certainly in all the contemporary developments, a different notion of entropy is also important. That's the microscopic or fine-grained von Neumann entropy. In contrast to thermodynamic entropy, von Neumann entropy is defined for a completely general quantum system. It's zero for a quantum system in a pure state, but for a quantum state in a mixed state described by an arbitrary density matrix rho, the von Neumann entropy is defined as minus the trace of rho log rho, where the trace is taken in the Hilbert space of the system. Now, the general relation between so von Neumann entropy is defined for any quantum system. Thermodynamic entropy really only makes sense for a system that's at least in local thermodynamic equilibrium. The general relation between von Neumann entropy and thermodynamic entropy is an inequality. The von Neumann entropy is no bigger than the thermodynamic entropy. To see this, consider a system that has n possible microstates given its macroscopic properties. So for brevity, here I will work in a microcanonical ensemble where we specify the values of the thermodynamic variables, such as the energy or anything else. And then there are n possible microstates. So the thermodynamic entropy is then log n. On the other hand, we can diagonalize the density matrix as a sum with coefficients pi of projectors onto pure states that I've called I. And the pi are non-negative because rho is a density matrices are positive, and the sum of the pi's is 1 because the trace of the density matrix is 1. So the pi's can be interpreted as probabilities that a measurement would find the system in the state I. Now, a simple calculation with Lagrange multipliers shows that the maximum, then what's been unfortunately truncated is that the entropy, which in general was minus the trace of rho log rho, once we diagonalize rho, it's minus the sum of pi log pi. I apologize to those on Zoom who won't see that formula, which I think I haven't copied at the top of the next slide. A simple calculation with Lagrange multipliers shows that the maximum of minus the sum of pi log pi under the constraint that the sum of the p's is 1 occurs when the p's are all equal and therefore are all equal to 1 over n. And in that case, the von Neumann entropy is log n, which is the same as the thermodynamic entropy. In general, since we had to maximize the von Neumann entropy to make it equal to the thermodynamic entropy, in general, the von Neumann entropy is less than the thermodynamic entropy. An important special case is a system consisting of two parts that I'll call A and B, with separate Hilbert spaces HA and AB, and the combined system has a Hilbert space HAB, which is the tensor product. Now, a general pure state psi AB of a composite system AB is not a simple product psi A tensor psi B of pure states of the two subsystems. Rather, it's an entangled sum of such tensor products. So the general form of a pure state of the combined system is like this. where I sub A or I sub B are pure states of system A or system B, and we can assume them to be orthonormal. And then the canonical form has positive constants, which I've called the square root of pi. The density matrices are then like so. And the von Neumann entropies are are equal, but unfortunately invisible. The von Neumann entropies are, again, minus the sum of pi log pi with these pi's. And the von Neumann entropies are equal for systems A and B because the two density matrices have the same eigenvalues. Now, the idea of understanding the Bekenstein-Hawking entropy in terms of entanglement entropy was first put forward by Raphael Sorkin in 1983. The idea was the following. In a quantum field theory, divide space into two systems A and B, which are going to correspond to the quantum fields in regions A and regions B will be our two subsystems. Let psi be the quantum state, which could just be the vacuum, and then let rho A be the reduced density matrix of the quantum fields reduced to system A. And so similarly, rho B is the density matrix for system B. So you can then try to calculate the density matrix. Sorry. I skipped too much over things that you couldn't quite see. In this special situation, because the entropy of system A and of system B arises purely because of the way they are entangled in a pure state of the combined system, in that particular situation, the entropy of systems A or system B is called entanglement entropy, an important special case of von Neumann entropy. Sorkin considered a pure state of the whole universe, the vacuum state, for example, or any other state, but let's say the vacuum state. It's a pure state of the whole universe, but to an observer who makes measurements only in region A or only in region B, it will look like a mixed state with entanglement between systems A and B. And Sorkin tried to calculate the entanglement entropy between the two systems. And he found it diverged, but the divergence was multiplied by the area of the boundary between them. Now, this was true for a completely general decomposition of space into two regions A and B, but Sorkin had in mind the application to the case that B is the black hole interior and A is the black hole exterior. And in that situation, he found an entanglement entropy that was proportional to the area of the boundary between them, which in the black hole case would be the horizon, but with an infinite coefficient. In modern language, his idea was that gravity would cut off the ultraviolet divergence, leaving an entanglement entropy that is the Bekenstein-Hawking entropy, the area not times infinity, but the area times 1 over 4g. So roughly, since Sorkin had ignored gravity in his calculation, that was like setting g to 0. And a times infinity is the correct answer as g goes to 0, according to Bekenstein and Hawking. And his idea was that with g non-zero, you would get a over 4g. This matches two intuitive ideas. One is that a over 4g is the irreducible entropy for someone who has access only to the region outside the horizon. That's what Sorkin did. In ordinary quantum field theory, he took the region outside the horizon, computed its entanglement entropy, and found that it was the area times something. Unfortunately, the area times infinity, but still the area times something. Two, the divergence in the entanglement entropy is proportional to the area because it comes from short wavelength modes near the horizon, which in Sorkin's calculation was the boundary between the two regions. As if, after cutting off the divergence, the density of quantum degrees of freedom on the horizon per unit area, well, there's 1 degree of freedom per g of area, as in Wheeler's picture, at least part of which you can all see. Now, more broadly, Sorkin's proposal can be motivated by reconsidering the derivation of the Hawking effect. The effect resulted from the ability to the late-time observer to see what's outside the horizon, but not what's behind the horizon. So the thermal nature of the late-time observer's observations came because the observer at late times is able to probe with arbitrary precision what's outside the horizon, but has no information at all of what's behind the horizon. So I think probably not tomorrow, but Wednesday, but maybe tomorrow afternoon, we're going to discuss why just being able to make observations in one region with perfect precision and nothing beyond that leads to thermal properties. Now, I'll tell you sort of one more result about the importance of von Neumann entropy. Susskind and Uglum in 1995 made a simple observation that strongly supports the idea of interpreting S out as entanglement entropy rather than thermodynamic entropy as Bekenstein originally assumed. If we interpret S out this way, the generalized entropy is better defined than either term on the right-hand side is separately. The second term has an ultraviolet divergence that Sorkin noted. But the first term also has a problem, although nobody noticed it before Susskind and Uglum. When Hawking had calculated his effect, and earlier, about 20 minutes ago when I was explaining to you his effect, neither Hawking nor we included loops of gravitons. And that meant that the Newton's constant that appeared in our formula was a bare Newton's constant, G0, without quantum corrections. But when we try to interpret this formula in the real world, we're presumably using the observed physical Newton's constant, since we don't know what the bare one was. And in quantum field theory, if you try to calculate the relation between the bare Newton's constant and the physical one, you run into an ultraviolet divergence, which at one loop order is a quadratic divergence. And Susskind and Uglum observed that at one loop order, the Sorkin divergence, we could call it, the quadratic divergence in S out, cancels the ultraviolet divergence in Newton's constant. So Susskind and Uglum observed that with S out understood as von Neumann entropy, the generalized entropy is ultraviolet finite. Their arguments were a bit crude, but it stood up with later work. It's been done more precisely, and I certainly will explain this point more precisely later this week. Now, von Neumann entropy has been very important in all developments in black hole thermodynamics following Susskind and Uglum. That's the last paper I'm going to tell you about tonight. For those of you concerned about the time, you might be relieved to hear that. That paper was in 1993, so this is 30 years ago still, 31 years. But although von Neumann entropy is important in all developments, it's not true that the Bekenstein-Hawking entropy, where A over 4G, where A is horizon area, is a von Neumann entropy. To see this, we can consider the time dependence of the entropy. Time dependence of an isolated system involves a unitary evolution of the density matrix. Rho is conjugated by a unitary. For example, U is e to the IHT for a system with a time-independent Hamiltonian H. Von Neumann entropy minus the trace of rho log rho is invariant under unitary conjugation. So the von Neumann entropy of an isolated system, like a star that will collapse to a black hole, or a black hole together with its surroundings, is time independent. By contrast, thermodynamic entropy obeys the second law, and it can increase, although you can't see the statement right there. So Bekenstein's idea from the beginning was that the A over 4G increases when the black hole swallows a table or chair or anything else. So since it can increase, and it increases dramatically, when a star collapses to a black hole, the thermodynamic entropy increases by a factor of 10 to the 20 or more, depending on the mass of the star. So the Bekenstein-Hawking entropy was a thermodynamic entropy, not a von Neumann entropy. But by now it's understood, and this will be hopefully something we'll get to toward the end of the week, that also von Neumann entropy is the area of something over 4G, but the something isn't the horizon in general. It's the area of another surface that's called the Ryu-Takanagi surface. That's one of the things I'll explain later this week. To conclude, following another paper from 1993, I'll just very briefly describe what happens to the thermodynamic entropy and the von Neumann entropy in the formation of a black hole by collapse of a star, followed by evaporation of the black hole. The reason for doing this is to tell you in another way what is the basic mystery about black hole thermodynamics. The star, to begin with, has a von Neumann entropy no bigger than its thermodynamic entropy, because that's true for every quantum system, as I explained. The collapse of the star to a black hole is a highly irreversible process in which the thermodynamic entropy increases by a huge factor. But it's presumed to be a unitary process in which the von Neumann entropy is unchanged. So in the real world, a black hole forms in a state of very small von Neumann entropy compared to its thermodynamic entropy. It forms almost in a pure state, a state of very low von Neumann entropy. When the black hole evaporates, its area decreases, so its thermodynamic entropy decreases. On the other hand, Hawking's analysis seems to show that the outgoing radiation from the black hole is purely thermal. That's the answer we found about half an hour ago, with a thermodynamic and von Neumann entropy that increases in time. The black hole is entangled with the radiation it emits, so its von Neumann entropy also increases, according to Hawking's analysis. As observed by Page, as the thermodynamic entropy of the black hole decreases, because the horizon area goes down, and the von Neumann entropy goes up, eventually the fundamental inequality between them is violated, and Hawking's calculation has to break down. And in fact, although it's slightly truncated, I think I had a reference to recent papers shedding some light on how to understand the breakdown of Hawking's calculation. However, to conclude what I've told you tonight, by now there's massive experience of which I've only scratched the surface in this lecture. In fact, I only will be able to scratch the surface this week, showing that black holes have a thermodynamic interpretation and that apparent irreversibility in black hole physics has the same statistical nature as irreversibility in everyday life. But there's only very partial understanding of what this means in terms of a microscopic description of quantum gravity. That's the puzzle that the work of Bekenstein, Hawking, and their predecessors, including many active researchers in this area today, have endowed upon us. Thank you.
Thanks a lot. Actually, we are a little short on microphones because only one is connected to Zoom. So I'll do it the very classic way without. And so I would encourage you, if you have questions, to shout as well. And we'll repeat the question for people on Zoom and then answer. Okay, that's the idea. So I don't have to run this time, which is good. Other questions? So there are questions.
Yes?
So when you're talking about von Neumann entropy, you assume the existence of a density matrix. Does the story change if you're in a quantum system, say with infinite numbers of degrees of freedom, where you have no sort of density matrix?
The question was a technical one having to do with the fact that in continuum quantum field theory, in general, density matrix is an oversimplified notion. The question, I think, was whether that would lead to a resolution of the puzzle. It's certainly believed not to, but you're invited to try to show that others have been wrong. However, I answered your question literally, but the fact that, the divergence in the entropy that Sorkin discovered when he first tried to calculate the entanglement entropy outside the horizon was related to what you've drawn attention to, that the density matrix isn't quite a valid notion in continuum quantum field theory that he assumed. Therefore, the fact that entropy is finite in gravity is a suggestion that density matrices are a better notion in gravity than they are in continuum quantum field theory. And there has been recent progress tending to show that, which I in fact did lecture about in Hamburg last year, but wasn't planning to go back to this time. Other questions?
You made the analogy about the cup of tea.
Yes.
It was sloshed.
Mm.
equilibrium. If one could say that one can learn about, the microstates
Mhm.
of your normal matter by observing that cup,
Yes.
then would one learn something about the microstates of the black hole in a sense?
Well,
From the bring down phase of the material of the black holes and the gravitational waves. Does that matter?
well, and so the question was, by watching the ring down of a black hole, do we learn something about its microstates? Well, if we watch suppose we pour the cup of tea into the glass. The analog of the ring down of the black hole is the sloshing of the cup of tea. And it teaches us about fluid mechanics. We could learn about the Navier-Stokes equation described by the water, but it doesn't truly teach us about the microscopic atomic state of the tea. So it's believed the analog of that is true for a black hole. So part of the story about black holes is that, well, it's most clear in the context of holography, but the oscillations of a black hole can be described by equations that are similar to the Navier-Stokes equations. And the ring down will teach us about that, but not truly about the microstates. However, there's something I really, didn't say about the cup of tea that I wish I had time to say, and I'm tempted to tell it to you now, just because you'd asked about the cup of tea, even though this isn't quite responsive to your question. Before we poured the cup of tea into the glass, it might have been described by a truly thermal density matrix with von Neumann and thermodynamic entropy equal. When we poured it into the glass, that was a unitary operation that didn't increase the von Neumann entropy, but it was irreversible, so it increased the thermodynamic entropy. So regardless of what was the case before we poured the cup of tea, after we pour it, it's not described microscopically by a truly thermal density matrix. Its thermodynamic entropy is bigger than its von Neumann entropy. And although it will appear to be in thermal equilibrium, if we could actually make very, very detailed fine-grained measurements involving correlations of all the Avogadro's number of molecules at the molecular and atomic level, we would have learned, well, in a fantasy world where you could do incredible things that are orders of magnitude beyond what's imaginable technologically, you would find out that it's not describable by a truly thermal density matrix. So that's kind of a miniature version. The star, even if it was in perfect thermal equilibrium, when it collapses to a black hole, the black hole has very low von Neumann entropy compared to its thermodynamic entropy. It's an apparent equilibrium as seen by outside, but it's not in microscopic equilibrium. Any other questions?
Getting a bit ahead, but in the Pacer story, saying that at late times,
Yes.
relation a thermal bigger than
Yes.
the Neumann, which is violated. But is that also not sensible because it's no longer a thermal equilibrium situation anyway? I mean, the interior of the black hole at late time.
Well, the inequality between von Neumann entropy, the question was, okay. When the black hole forms from collapse, it's born with small von Neumann entropy compared to a much bigger thermodynamic entropy. As it evaporates, one goes down and one goes up. And then if we follow Hawking's calculation, we eventually reach a contradiction first pointed out by Page. The question that was asked was whether the contradiction can be avoided by taking advantage of the fact that the black hole might not be a truly thermal system. Well, no, this inequality is universal inequality for quantum systems. So no matter what you assume about the black hole, as long as it is a thermal system, it can never have a von Neumann entropy bigger than its thermodynamic entropy. So if Bekenstein and Hawking are correct for the thermodynamic entropy, and Hawking is correct for the von Neumann entropy, then something has to change. Unfortunately, this week, I'm going to explain, I think, everything you need to know to learn that story, but well, we'll see whether we actually get the chance to explain that story. I'm not sure we will.
You mentioned the information paradox. I was waiting for it the whole time.
Well, I didn't use the phrase information paradox.
Sorry?
I didn't, the question is why I didn't talk about the information paradox. I didn't use the phrase information paradox, but I told you a couple things that I explained. I would say I explained the information paradox. So uh, the black hole formed possibly from a star in a pure state. So if the laws of nature are reversible, then from the decay products when the black hole evaporates, they must contain all the information needed to reconstruct the original star and its detailed microstate by running the equation backwards. But according to Hawking, the final state appears to just be thermal. That's the information paradox. Or in Page's formulation, the information paradox arises if we assume that the black hole is a quantum system to which the universal relations, properties of von Neumann entropy apply. So its von Neumann entropy then must grow with the von Neumann entropy of the outgoing radiation because they're entangled. I'll explain this more precisely in a couple of days, but that's the basic idea. And its thermodynamic entropy is going down because its area is going down. And eventually the basic inequality that the von Neumann entropy can't be bigger than the thermodynamic entropy is violated. That's Page's formulation of the information paradox. So, well, I would say I explained two typical manifestations of the information paradox, but it's true I didn't use the phrase information paradox. Yes, I see a question.
Is there any hope that we can know something about microstates of normal black holes, either like supersymmetry breaking without using
The question is basically the following. For certain supersymmetric black holes, we have a very detailed understanding of the microstates, accounting for the Bekenstein-Hawking entropy. So with a huge number of microstates, e to the a over 4g, where a is the area. This was first done by Strominger and Waffe in a special case around in 1995 or 6. And since then, there's been a lot of work with more detailed calculations, including quantum corrections to the Bekenstein-Hawking formula and all different kinds of supersymmetric black holes. So there's a lot of wisdom there, but very little insight about similar results for non-supersymmetric black holes to answer your questions. And if anything, the modern ideas suggest that there can't be a similar picture.
how could one establish the quantum nature of black holes experimentally in principle?
Well, if you could observe Hawking radiation, that would be rather compelling. In cosmology, we observe something that's believed to be similar in the fluctuations that make up the fluctuations in the cosmic microwave temperature, which are believed to have been the seeds of formation of galaxies and clusters of galaxies. To establish in a really very, very convincing way that okay, if I was to have explained the theory of those fluctuations, it would be clear that it's quite analogous to the theory of black hole evaporation. What would really clinch the case for the fact that the cosmic microwave fluctuations have the origin that they're believed to have would be if we could observe verify a further prediction, such as the gravitational wave fluctuations that are also predicted to have come out of inflation, or possibly the non-Gaussianity of the CMB fluctuations. So for now, the best I can say is that there are reasonable grounds to believe that we've observed something that's analogous to Hawking radiation. However, to answer your question literally about black holes, the best we could hope, and it's kind of far-fetched, well, if there were miniature black holes left over from the Big Bang, or if the outer solar system contained a black hole, which has also been a subject of some speculation, then conceivably, futuristically, we could observe Hawking radiation coming from a black hole. As for whether it would test the quantum nature, it's a prediction of the quantum theory of black holes. But if you wanted a test at the level at which Bell's inequality shows that certain things can't possibly be described quantum mechanically, I'm afraid even observing Hawking radiation would fall short of that. I wasn't quite sure of what degree of confidence of the test of quantum nature of black holes you wanted. I need even more fanciful thought experiments if you wanted to test Bell's inequalities in black holes. I won't try to figure out how to do it right now. Any other questions?
Seem to be some on Zoom.
There's, we can go to Zoom, but there's one up here.
Question about the field. How the operation of black holes is connected to charge conservation, because I mean this the area decrease, so how the charge.
Well, the question is what formation and evaporation of the black hole has to do with charge conservation. So for electric charge conservation, the answer is nothing. The process conserves electric charge. The reason it does and has to is that the electric charge can be measured by the electric field at infinity far away, and whatever happens in the interior can't change it. So you get a real contradiction if you thought that black hole physics was violating electric charge conservation. But baryon number is another story. So a black hole in the real world forms from matter from a star that's rich in baryons. Then when the black hole evaporates, since the temperature is so low compared to atomic temperatures, that's something I should have stressed more in the lecture. What comes out of the black hole are almost exclusively massless particles for almost the whole life of the black hole. So in particular, baryons don't come out with any significant number. And at the end, Hawking's calculation will break down, the temperature goes up. The temperature of the black hole was inversely proportional to the mass. So it's very, very low for astrophysical black hole. After the black hole has mostly evaporated, eventually the temperature is high enough to emit baryons, but by then the mass is almost all gone and very few baryons come out. So formation and evaporation of a black hole drastically violates conservation of baryon number. But that poses no contradiction because baryon number cannot be measured by measuring something at infinity. It's only what's called a global quantum number. And in fact, particle physicists have come to believe that ordinary local laws of nature violate baryon number conservation, even without black holes, although it hasn't yet been proved experimentally, as we hope to ultimately prove. Okay, if there are questions on Zoom, maybe we should go to Zoom.
Right, maybe one I would think of two, and then I would also encourage people who actually attend the lecture series to maybe ask more questions then, because we are slowly approaching 90 minutes, but yes.
Ah, I'd have worried less when I was talking if I'd known 90 minutes was the.
No.
Okay.
Okay, I will read one of the questions.
Yes.
Is it straightforward to connect the thermodynamic nature to information theory, for example, by using Shannon formula? If yes, to the thermodynamic entropy or to the von Neumann one?
Well, the question was whether information theory, classical or quantum, is applicable to black hole quantum physics. And the answer, very good question, actually. And the answer is that ideas from quantum information theory have turned out to have echoes in black holes that are quite uncanny. That's part of what I meant when I said about 45 minutes ago that Einstein's classical theory seems to have an uncanny knowledge about the fact that it's going to ultimately be quantized and compared to quantum phenomena. So phenomena in quantum information theory have had amazing links with phenomena in black hole physics. I've barely said a little bit of it today because the von Neumann entropy is a basic concept in quantum information theory. And I said it's the area of something divided by 4G, but tonight I didn't say what the something is. We will explain it in a couple of days. But there are many, many more detailed things, most of which I actually won't be able to get to this week, where in detail quantum information theory has had echoes in black hole physics. So when I told you that even with 6 more lectures, I will only scratch the surface of what's been done in this area, that's what I was thinking about.
Maybe a final question I would suggest.
Yes, I wanted to know, is there any research to try to simulate quantum gravity in a neural networking without to see the microscopic particle as in a neural networking to see how it would be work as a system and then combine the detailed graph.
Well, the question was, can we learn something by simulating a quantum black hole in a neural network? Well, we can only do that to the extent that we have microscopic equations that we think we describe black holes. And to some extent we do, although I haven't explained it tonight, in the matrix model of M theory and in holographic models of certain black holes. Even with today's computers, the ability to simulate them, either with neural networks or otherwise, is pretty limited. So not much has been done successfully, but it is true in principle that more could be done and maybe will be practical in the future. There certainly are equations we'd like to simulate, but we can't. Or, well, to a very limited extent, something has been done. Some things have been tested, but limited. So are we, okay.
Now, that's that we slowly come to an end, right?